Today we will be working on inverse functions. We'll find them algebraically and we'll graph and do some comparing as well. What is an inverse function? Inverse function is a function that basically undoes another function. So for example, if you have f of x equals x plus 4. When you go and think of this in terms of a t-chart, you can plug numbers in 1, 2, 3, and 4, and then what happens? You get outputs of 5, 6, 7, and 8. Well, what function undoes that one? Well, x plus 4, the inverse of that, to undo it from adding 4 would be to subtract 4. What I want you to pay attention to when I set up this t-chart here is now instead of plugging in the numbers 1, 2, 3, 4, I'm actually going to plug in 5, 6, 7, and 8, and then look what happens. So your domain from the first function has become the range of the second, and your range from the first has become the domain of the second. And since these are inverse functions, that will happen with all inverse functions. That's not a proof to it, but that's what will happen. What is the relationship between the domain and range of the function and its inverse? And just like I said, the domain of the function will be the range of its inverse and vice versa, which is very important because if we know the inverse, then we can also help us find the range of the original as well if we know what the domain is. So since inverse functions undo each other, then when you compose two inverses, the result is the input value of x. So this part right here where it's showing the algebraic side, f of g of x will be equal to g of f of x, and then those two will be equal to x. So if we want to prove that two functions are inverses, we can prove them by compositions. But once again, you have to find both of them, f of g of x and g of f of x, and if they equal x, then the two functions will be inverses. So on example 1, I'll go back and do this in the example video, but here would be an example of two functions that I would want you to prove whether they are inverses of each other or not. We will be doing example 1, are these functions inverses of each other? So we'll be using the algebraic way of proving if they're inverses by compositions. So we're going to start by finding f of g of x and see if that's equivalent to x. So it would be f of g of x is 5x plus 3 divided by 2. Then we'll take that and plug it in wherever there's an x in the f function. So it'll be 2 times this whole quantity, 5x plus 3 over 2, minus 3 over 5. So don't forget the rest of the part of the function f of x. Now the 2's cancel there, so that'll be left with 5x plus 3 minus 3 all over 5. The 3's cancel, and so it's 5x divided by 5. The 5 cancels, and you are left with x. So f of g of x is equal to x. So that's good. Now, if it didn't, we would be done and say they're not inverses of each other. But since they are, we will continue and find now g of f of x. So we'll switch it around. So now we'll do g of, and then the f function is 2x minus 3 over 5. So wherever there's an x in the g, we're going to plug in this expression. So it'll be 5 times 2x minus 3 over 5. And then that's all minus 3 over 2. So 5 times 2x minus 3 over 5, that's supposed to be a plus 3 divided by 2. So the 5's cancel. That leaves us with 2x minus 3 plus 3 divided by 2. The 3's cancel, so 2x divided by 2. The 2's cancel, so it is equal to x. So are these inverses of each other? The answer is yes, they are inverses. F of x and g of x are inverses. Because f of g of x is equal to g of f of x, which is equal to x. So that's the reason why they are inverses of each other. On this next part, I want you to graph an inverse. And what I've done so far is I've just plotted 5 points. And what I want you to do is I want you to graph the inverse of those 5 points. Well, how do I graph the inverse if all I have is points? Well, remember, domain and range switch. So if you have this point right here at 2, 7, then its inverse will be 7, 2. So that'll be located right there. And do that for all 4 points. And then we're going to take a look and see what is going on with the inverse when you graph it. So now I have all the points plotted and their inverse points. And what I want you to look at is, what do you notice about those when you just take the domain and range and switch them? And what happens is the inverse functions will be symmetric about the line y equals x. So I'm going to draw in the best y equals x line I can on here and see if you can see that reflection. And so now that I have that line drawn in, look at the points. Look at 7, 2, and 2, 7. See how they look symmetric to each other? And do that with kind of all the points. And you can see, so when you graph an inverse and you switch that domain and range, inverse functions will always be symmetric about the line y equals x. So now just kind of some information about inverses. To have an inverse function, a function must be what we call one-to-one. All right, and that's, so if you have a function and you want to find its inverse to be a function, it has to be what we call one-to-one. What is one-to-one? Well, one-to-one is that no two elements in the domain of f correspond to the same element in the range of f. So once again, read that again. No two elements in the domain of f correspond to the same element in the range of f. So if you recall, a vertical line test can help you determine whether a relation is a function. Well, similarly, the horizontal line test can help you determine whether the inverse of a function is a function. So for a relation to have an inverse, the function or the relation needs to be one-to-one. It needs to pass the vertical line test to be a function, and then it has to pass the horizontal line test so that its inverse will also be a function. So for example, maybe not the best drawing, but the idea is with a quadratic, if you rotate that and you go symmetric to the line y equals x, even though this one is a function, if you do its inverse, does this pass the vertical line test now? No. So because it didn't pass the horizontal line test up here, it won't pass the vertical line test when you do its inverse. And that's why it must be one-to-one. So what kind of functions do we have that are one-to-one? You have square root functions. All right. Lines or linear are one-to-one. Cubics are one-to-one. So we have some functions that are one-to-one, and then we have some like the quadratic or also the absolute value that are not one-to-one, and we'll have to put restrictions in place to be able to find their inverses. So to be able to find inverses algebraically, if you kind of think about it, you can go through and figure out that your f of x represents your y. So if you replace f of x with y, and then when you find the inverse, remember you're taking your domain and range, switching it. So we're going to interchange our x's and y's, and then we're going to solve for the new y, all right, which would have been the domain of the other one. And now at the end, you want to rewrite it as an inverse. So you want to make sure that you use that f, and it looks like you're raising it to a -1, but that's how you indicate the inverse of a function. Okay, so there's two examples. One's a square root function, another one is a rational function. Once again, I'll do both of these on the example video. The next part that we're going to be looking at is we're actually going to find inverses algebraically. So we're not going to prove their inverses on this one, we're just going to find them. So on the first one, f of x is equal to the square root of 2x minus 1. So what do we need to do? We need to replace the f of x with y. We need to exchange or interchange the x and the y value, and then solve for y. So how do we get, you just got to work backwards. You got to get rid of the square root, so we square both sides. You add the 1, and then divide by the 2. So that leaves us with y is equal to x squared plus 1 over 2. We do want to write it as the inverse. So we're going to change it back to function notation, f of x, but we're going to use that -1 as the inverse, is equal to x squared plus 1 over 2. Now I want you to look at that for a second and see if you notice anything that we need to fix. So the domain of the original function was all values greater than or equal to 1/2, and its range was all values greater than or equal to 0. Well, why does that matter? Well, the inverse had an x squared. So if you remember, a quadratic is a parabola. Is that a one-to-one function? No. So we have to have some type of restriction here for our domain. So what values of x must we only include? We can't include all real numbers. So if you look here, the range was all values greater than or equal to 0. So our domain for the inverse must be all values that are greater than or equal to 0. So that might be something we need to work on in terms of identifying that, but remember, they have to be one-to-one functions. The original one, f of x, was. The inverse, when we solved it algebraically, was not, so we had to fix it. All right, let's take a look at example B. G of x is equal to 2x minus 3 divided by 5x plus 2. All right, with the second example, we'll start it the same way. We will say y is equal to 2x minus 3 over 5x plus 2, replace the x and y, exchange them out, so x is equal to 2y minus 3 over 5y plus 2. Now this one has two y values in it, so we're going to have to see what's going on here, but let's first just go ahead and take care of some things. Let's get rid of the denominator, so we'll multiply by the quantity 5y plus 2, so that'll be x times 5y plus 2 is equal to 2y minus 3. Let's go ahead and distribute. So 5xy plus 2x is equal to 2y minus 3. Now normally when we have two y's in the problem, we want to get them on the same side. So let's do that. Let's subtract the 2y to this side. Let's also move the 2x, since we don't need that, since it doesn't have a y in it. Let's subtract the 2x to the other side. So we're kind of doing two things here. So that leaves us with 5xy minus 2y, and we're also going to subtract the 2x, so minus is equal to negative 2x minus 3. Now, with something like this, we would normally try to combine like terms, but you can't combine them. So what is another way that you can get one y from two y's that are being added? Think about that for a second. All right, so if you figured it out, we use the distributive property, or what you might call factoring the y out, and you're left with y times 5x minus 2. Well, why is that helpful? Because now we have one y compared to 2, and then it's y times that, so we can divide everything by 5x minus 2. So we get y is equal to negative 2x minus 3 over 5x minus 2. So the inverse, g of x, so g of x, the inverse of g of x is equal to negative 2x minus 3 over 5x minus 2. And then that is the inverse of the original. Now, this one doesn't have a restriction in terms of the domain. This is a one-to-one function. They're both rational as well. So the last example that I have, I'm actually going to go ahead and do this. It kind of goes through a lot of the different things we talked about. Graphing a function, finding the inverse, and then graphing the inverse as well. So f of x equals x squared minus 3, but we put a restriction where x must be greater than 0. And the reason we did that was because if we didn't, it wouldn't have been a one-to-one function. So we only want values that are greater than or equal to 0. So you could use a t-chart, or you could use transformations, realizing that the graph gets shifted down 3 units. So your vertex is now at 0, 3, and then you could graph the rest of the points from there. Or you could use your your table, plug in 0, get negative 3, plug in 1, you get negative 2, plug in 2, you get 1, plug in 3, and you get 6. So you get the same thing. However you want to graph the function, that's up to you. So we'll graph the function, and since we're going to graph two things on one graph, we want to identify that this is the f of x function. We want to find the inverse of the function. So to find the inverse, we say y is equal to x squared minus 3. We interchange the x and y's. That's your domain and range. And now we're going to solve for y. So you add 3. And since it's squared, you take the square root. So y is equal to. And normally we would put plus or minus. But if we do plus or minus, it won't be a function, and we have the restriction where before x was greater than or equal to 0, so we have to hold that true for the inverse. And so finally, we'll say that the inverse of f is equal to the square root of x plus 3. So really that second part is done. We graphed the function, we've now found the inverse, and now we need to graph the inverse. Now what we could do is we could take this graph and say, okay, well the radical or the square root function gets shifted to the left 3. We could do a table if we wanted to and plug in the values that would be appropriate for a square root, or you already have the table. The table's right up here. It's the same thing because all we have to now do is make our range from the original the domain and then switch them. And so you can really just take these points that you had before, 0, -3, and now graph -3, 0. 1, -2 is now -2, 1. 2, 1 is 1, 2. And 3, 6 is 6, 3. And there is your inverse function. And I've also drawn in the line y equals x because it should be symmetric to that, and you can see that it is. And so we graphed the function, we found the inverse, and we graphed the inverse as well. So that'll be it for inverse of functions. I'll go back and finish the examples on another video.